Hi friends, today we're going to talk about uplift modeling using meta-learners. Specifically, we'll talk about three meta-learners, which is S-learner, T-learner, and X-learner. First of all, what is uplifting model? What is causal inference? So the difference is that compared to a prediction model that usually just predict response, a causal inference will predict the uplift effect. Here is a concrete example. So in the situation of digital ads, you have a choice of whether to show this ad to the user or not show this ad to the user. And it's a budget constraint problem in that you only have that many impressions you can show to the user, and the user's attention is limited. So whether to show or not show the ads can be considered as control and treatment. So the treatment is showing the ads and the control is not show the ads. The outcome is whether the user purchase or not. So essentially, if it is a regular prediction model, the model will only predict whether user purchase the item. But for causal inference, what we want to understand is that the expected outcome difference between control and treatment. Essentially, we want to measure and estimate the effect of the treatment. So it is not the final response that matters. What we want to understand is that by showing this as, how much more likely will the user purchase the item? This is essentially the problem setup for causal inference. We will start from the most straightforward meta-learner called S-learner, single model estimate. It is called single model because it takes both the user features and the treatment indicator W as features. So it takes these input features and predicts the expected outcome, for example, user purchase or not. And then it measures the uplift effect by doing the inference 2 times. In our example, this could mean that the user was shown the ads, and this is the estimate of whether the user will purchase. And this is a control group where you set W equals to 0, and we're estimating whether this user will purchase the item. And uplift essentially is a delta of these. So this measures the effect of users' expected response given the treatment intervention. So far so good. The only thing here is that you use treatment indicator as a feature. So when you are training the model, this treatment feature might be ignored, so causing that model actually cannot learn the delta, the uplift. So this is the reason why we have T-learner, basically two models. We split the data into two groups. One are the subjects that are in control, one are the subjects that are in the treatment. And we build two models. At inference time, we just calculate the delta. So for the same user feature, you run inference in the treatment model that predicts the expected outcome if this user is in a treatment group. And similarly, you run the user feature for the control model, and you get the expected response of user if it's in a control group. And the delta is the expected uplift. So this sounds good too, right? But there's also another drawback. The drawback is that what if that majority of the data is in control and very few data is in treatment? So if you have less data in treatment, that just means that your model is not as trustworthy. This is essentially the motivation of X learners. X learner is trying to solve this imbalanced data problem. So essentially, it is doing this by 3 steps. The first step is to estimate response functions. This part is similar to T-learners. Essentially, we have two models and trained on separate data. One is control model trained on control data. The other is treatment model is trained on treatment data. And secondly, we'll compute the treatment effects. And to give you a concrete example, if a user is in treatment group, that means you have true label for its treatment group. That is why they use the control model as estimator. So this data here essentially is our expected uplift. So similarly, if a user is in control group, they'll use the treatment model as estimator. So far so good. This is our estimated treatment effects. But the third step is the most important is how X learner shines. It trains its propensity score. Essentially, The propensity score estimates the likelihood of this user being assigned the control and treatment in the data. Think of this way. The problem that XLearner is trying to solve is imbalanced data. So if given these user features, you predict that the user in the original dataset is very likely to be in the treatment, then that means the treatment estimator is very trustworthy. So here, with this propensity score, we're able to weigh the trustworthiness of the estimators. So here is the final equation of the expected uplift. Here is a quick summary of what we just talked about. Starting from the simplest XLearner, which use one model and takes both user features and treatment indicator as input features. And then we go from there to T-learners, which can better learn the difference between control and treatment by using two separate models, one for control and one for treatment. This solves the problem of how to distinguish control and treatment, but also encourage another problem that this method might not be stable because of imbalanced data, which is how we use XLearner to solve. XLearner solves this by having a dedicated propensity score that can weigh the trustworthy of the estimator. So even though XLearner sounds very powerful, but it can be complex and takes longer time to implement. So XLearner and T-learner are also a good starting point. So that's it. Thank you for watching. We'll see you next time.